Kids, time for some inverse Laplace, right? That's kind of crazy. So what if I give you a function that I've already transformed and I want you to go backwards, right? It's the classic undo situation, right? So here's capital F in terms of S, and that was a Laplace transformation of little f, right, in terms of t. The whole idea of Laplace, take a function in terms of t, rewrite it in terms of s, do algebra. So what if I, though, take the inverse of the Laplace, which means, right, how do I undo the Laplace? What if I want to get f of t by itself? Well, don't you just, anytime you're taking an inverse, right, use inverse notation? Do the same thing, though, to this side. So what happens to the right side? Laplace inverse with Laplace is going to undo one another, and just f of t is going to drop out. And then we have the inverse Laplace of cap f of s, right? Hopefully that makes sense. We're taking Laplace and undoing him, right? It's the inverse. Do you see that? Do you see that? See what I did there? So you want to write this down in your notes. And hopefully you can see where we're going with this, right? We haven't done any differential equation stuff yet. We have just learned some definitions, right? Where did some of the Laplace transforms come from, right? Improper at its heart, Laplace is an improper integral, right? And we built some of the table entries ourselves, and then and then practiced with them, going from a function in terms of t to a function in terms of s, using the transform and then not doing the transform ourselves, but just matching the table, Laplace's table. And now I want to try to learn to go backwards. Just like with the going from f of t to f of s, we used some properties. We have similar properties for inverse transforms, right? The inverse transform of constants times, right, the sum of constants times these transform functions. Oh, that G isn't purple. You can osmosis out constants, and you can break up sums or differences. Right, I really should have put a minus under here as well. And that should be purple. I mean, it's the details, right? Okay. So if I give you a transformed function and I ask you to find the inverse, what do you do? So the first thing you want to do certainly is work with your handy dandy, right? You hear that? My handy dandy table. Should have my handy dandy table with me. And yes, you will have your handy dandy table on assessments. So can you look at this with your table and match? Now I am going to break this up into 3 problems. Further, I'm going to kind of sort of look at this like this. I'm going to say officially that 6 times 1 over s minus 1 over s minus 8 plus 4 times 1 over s minus 3. And then I'm going to look at my table. What do you see there? 1 over s. What is it equal to? Right? Just 1. So I'm going to replace that with a 1. Of course, bring down the 6. Minus what? There's 1 over s minus a. Do you see that form? And what is that? Right? So I'm going to replace this whole thing with e to the what? To the 8t or negative 8t? 8t, right? Because that minus 8 is a. Four times this is now not equal to f of s. What is it equal to? little f of t going backwards. Cool beans. Let's do another one. So it's super nice when everything matches up with my table like that. So that is always step one. Step one is always look at the table. So this is capital F of S. Do you see it in the table? So scan, right, the second column and look for, do I see an S times an S squared plus 1S in the denominator? And generally I do look at the denominator first. I look at the denominator first and say, do I have S squared? There's an S squared plus, no, nope, there's no S out front. No, darn it. No, right? So I'm looking at my table and I don't see it. And again, generally I am looking at my denominator first. It's more complicated, right? And then looking, if I find the denominator, I'll look to see if I can manipulate the numerator. Well, what do I do here? So f of s is equal to 1 over s times s squared plus 1. Well, since I don't recognize the denominator, maybe I need to rewrite this. How do I rewrite this? What's one thing I can do? I certainly can't factor s squared plus 1. You got it, baby. It's partial fractions. Partial fractions coming back. Oh, my Lanta. So this is something. I have s and s squared plus 1 because you know what? You know what kind of led me to that thought process? I do have things in a table with just a denominator of s, and I do have things in my table with a denominator of s squared plus a squared, don't I? So, yep, that's what gave me the clue to do. Now, remember, when you have a quadratic here, your numerator has to be s plus c. And then, of course, doing my partial fraction work. Right, and now I'm going to combine stuff. So what does this mean? A plus b are coefficients of s squared. C is the coefficient of s. And a is the constant. And remember, over here I have 0s squared plus 0s plus 1. So therefore, hopefully you can see that a is equal to 1. C is equal to 0. A plus b is equal to 0. But we already know that a is 1. So b has got to be negative 1. So that helps me up here rewrite f of s, which is 1 over s times s squared plus 1, can be rewritten as a over s plus b, which is negative 1. So I'll have negative 1 s plus 0, right? So I think I'm just going to write this as negative 1 over s squared plus 1. And now let's go to the table. I think we already recognize that, right, from the last problem. But what about this? Do you see any denominator in your table where you have an s squared plus something? Yeah. You have two places. You have sine and cosine. S squared plus a squared. So who's a? Right, that's a. So if that's a is 1, 1 is on top. So sine or cosine, who is that? That's cosine, right? So now I can write f of t, little f of t transformed back. 1 over s by the table is just 1, minus 1 over s squared plus 1 is cosine of at. What's our a? And no, of course, you don't have to write the 1. I now have a function, right? Starting with a function in terms of s, I transformed it back into little f of t. That looks so, it does not look attractive, sorry. All right, let's do another one. Maybe you can see what's coming here, right? You certainly don't, I certainly in my table don't see anything like this. Again, step 1 is I look at the denominator and I look at my table. Now, something I do think about though, just because I don't see an expanded trinomial, but if you scan down there, you see some s minus a squares and some s plus a all squared, which I can expand to a polynomial, right? So this one doesn't, this one has just been expanded, but it doesn't look like a perfect square, does it? Oh, 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 oh. Can you make it a perfect square? Firstly, I looked at, so let's see, let me write some stuff down. I looked at the denominator, and the first thing I did is look at the table. And I didn't see anything that matched it. Then I thought to myself, well, can I factor that quadratic nicely? Right? Because do I look at, when I look at my table, I do see some denominators that have, right, just have some factors in it, right? Or I can split up again. If I can factor this, I can use partial factors and split it up. I don't see that. Can I complete the square? Especially with a numerator of 1. What if I do that? Let's see what happens when I do that. So f of s is equal to 1 over s squared plus 6s plus 13. What happens when you complete the square, right? You need to divide 6 by 3, square it, and add 9. So if I add 9 here, how do I have to balance that? I don't have an equation where I can just add 9 to the other side. Yeah, balance it out right here in your expression by subtracting by 9. How does that help? Factor your perfect square trinomial. Plus what? Plus 4. Okay, this is now f of s. So I did this. Now go back and look at your table. Do you see anything that has a perfect square trinomial with a plus in it and then followed by a plus something else? Let me get out my table here. As I scroll down, ooh, that kind of looks like, what, 19 or 20? Oh, crap, those are minuses. Oh, that's okay. That's okay. So firstly, look at 19 or 20. With a numerator of 1 instead of a numerator of s minus n, instead of, right, a term here. So who does this look like, 19 or 20? Kind of looks like number 19, right? So let's see if we can manipulate ourselves. Right, number 19 from the table looks like this. B over s minus a quantity squared plus b squared. So let's see, what can I do? Okay, so Let's first look at s plus 3. Oh, snap. I'm so clever. So proud of myself. You see what I did there? Now, how about this 4? I want to match this form. What do I make that 4? Excellent, excellent. So at this point, what do I have? -3 is my A. 2 is my B. In order to match this form, what do I have to have in my numerator? I have to have a 2, right? But I don't. How can I see what you want and legally make it happen? I want a 2 up there. That's not legal. Until I do what? That. So, look at what I'm going to do over here. I am going to write f of s as 1/2 times 2 over s minus -3 squared plus 2 squared. And now I have, again, here's my A equals -3, B equals 2, B equals 2. So now I can rewrite, or not rewrite, write little f in terms of t is just 1/2 times who? E to the -3t times cosine of, I'm sorry, sine, number 19, right? Sine of bt. So here's my A, and here's my B. Crazy, right? Crazy. Let's do another one. All right, check this one out. So look at your denominator. Oh, I didn't really want that to be red. Look at your denominator. It's in, right, expanded, right? It's an expanded quadratic, right? Can you factor it? Can you complete the square with it? Right, if I can factor it, then I'm thinking that, oh, I might be able to use partial fractions and split it up into 2 easier fractions to look at instead of 1. So I looked at this and I was like, oh, no, that doesn't, right? 7 and 3, 21 and 1 doesn't really factor. So again, I looked at the table. Oh, I don't want to be red first. I looked at the table. The denominator for the table didn't get a match. Then I thought, can I factor and do partial fractions? Nah, that didn't work. So can I complete the square? I mean, I can always complete the square, but can I complete the square? And it helps. Let's see. So my denominator is s squared plus 8s plus 21. And I have 1 minus 3s in my numerator. Divide by 4 square. Divide by 4. Divide by 2 and square, I meant. Which means you have to subtract 16, right? What do I have now? Plus 5, right? All right, so now go back. Now focus on your denominator again and go match. Right, go to my table. Who does this look like? I'm not scared by that plus, right? I'm not scared by that plus anymore. I know what I'm going to do. I'm going to make that s minus -4, right? I got that. But what about that 5? What about that? What is that 5? And then by the way, what the heck is up with that numerator? Right, I got too much going on there. So, all right, well, I still am kind of focusing on 19 and 20. Because of the denominator. So, but when I'm looking at the denominator, I am okay with the fact that I'm going to make a -4, right? But what about b? Is b equal to 5? I don't think so. What is b equal to? √5. All right, all right. Now that numerator. When I look at 19 and 20, the difference is that 19 has only a single number, and it's got to be a √5 in that numerator. That was a little challenging. Then I look at 20, and 20 has s minus √5. What the heck? No, 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 no. Look at number 20 again. Is that s minus √5? No, that's s minus a. Ooh, and a is an, All right. Let me focus on the numerator now. Let me do some stuff with this numerator. Some things that might not occur to you. Look at that numerator. Again, what I'm focused on is 19 and 20, and the numerator of 19 is b, which is √5. The numerator of 20 is s minus -4, which would be s plus 4. So my goal, I'm going to focus on that first because I can't figure out what to do with the √5 right now. But I'm going to look at 1 minus 3s and say, well, could I turn that into a group where it's s plus 4? Well, certainly not right now. So I'm just going to focus on the numerator here. Look at what I'm going to do. I'm going to rewrite this as -3. I'm just going to write s, -3s plus 1, right? That's what I did first. Now, what I really, really, really want, though, is I don't want -3s plus 1. I want s plus 4. Again, see what you want and legally make it happen. What if I really want an s plus 4 in there? That's what I really want. I want an s plus 4. How can I make the s plus 4 equal what I originally had? There's -3s, but what do I get here? That's -12. So if I have actually inserted a -12 into the numerator, how do I balance that out? Add 12, baby. Hey, don't forget something. Who did I forget? I added negative, but don't forget this. I already had a plus 1 out here. Right? So -3, -3s minus 12 plus 12 is going to go away, and then I'm going to have my plus 1. So how did that help me? So I have -3 s plus 4 plus 13 all on top of, wait, does it have to all be on top of? Right? What if I do this? Oh, snap. Now, how has that helped? Has that helped? Who does that look like? Rats, I wanted that to be yellow. Go to your table. Who does that look like? With what in the numerator? Oh, that -3. Oh, hey, snap, watch. It's kind of in my way, right? Who is this? Do you recognize it from your table? A is not 4. What is A? -4. B is √5. And for number what? Not 19, but number 20. Number 20, what does the numerator have to be? S minus A. I did it. I did it for half of the problem. So over here, f of s who is this part going to be? This is going to be number 20, right? And number 20 is e to the at cosine of bt. Feel pretty good. All right, let's go back and look at my second part. So I recognize that, my denominator, same A, same B, but who does this, with just a single number in the numerator and nothing I can really do with 13, I don't have a variable up there at all. See, up here, when I had an S, I was able, right, to kind of go to the cosine formula because it had an S in the numerator. This is just a constant, right, and I have no way of getting an S in there. So I'm thinking 19. But in order to be 19, and to fit the form of 19, √13 has to be a √5. Well, see what you want and legally make it happen. I can only multiply that 13 by 1. So look at my clever 1. Math can be so sneaky. How does that help? Do you see? What do I want? Who do I want in that numerator? I only want to keep the √5. I only want that to stay in my numerator. So guess what I'm going to do with the 13 √5? Ha! I'm going to take 13 √5 and put it out front. So capital F of S is going to look like 13 over √5 times the √5 that I left in that numerator, S minus -4 quantity squared plus 5. So who is that? 13 over √5 e to the -4t, because a is -4, but not cosine this time, sine of b t. Whoa. Apparently my pen is not cool. Attempting to write math is so cool. But my pen, not having it right now. Pretty darn neat. All right, so I've given you some problems to do in the book that practices this. And honestly, right, it's the whole idea behind Laplace is to get to algebra. But the algebra is, right, pretty substantial. So, and gets even more substantial than we're going to fairly quickly. But we're going to learn just the, right, we're going to just learn a couple of the basics of these inverse transforms. And then we are finally ready to go on in our next live session to using Laplace to solve some differential equations. So we'll do some more with inverse and go on to the next section in our next live session. See you then.